The next topic we're going to talk about with identities are the sum and difference identities for the cosine. I have a couple images up here, or diagrams, that we'll be discussing. It's going to help us to understand what's going on here. But basically, the idea is this: if you were to have, if you were to take two angles and add them or subtract them inside of a trig function, for instance, and we'll use the cosine as an example because that's where we'll start. If you had something like the cosine of 15 degrees plus 23 degrees, for instance, this is obviously, well, 15 plus 23 is, what's that, 38, right? This is obviously cosine of 38 degrees. Let's write it this way. Equals the cosine of 38 degrees. Now, if you calculate this cosine, you get a decimal answer, and you could do that with a calculator, just very briefly. The cosine of 38 degrees, and make sure I'm in degree mode, which I am, is approximately 0.788 if I round to the nearest thousandth, okay? However, some people will try to split this cosine up. It's not valid, okay? And what they'll try to do is to write it as a cosine of 15 degrees plus a cosine of 23 degrees. Well, of course, these two expressions are not equal to each other, okay? You can't just take a cosine and split it up some weird way like this. I can prove it to you. If I calculate the cosine of 15 degrees, that's approximately 0.966 rounded to the nearest thousandth. And if I calculate the cosine of 23 degrees, well, that's approximately 0.921. And if I add them together, definitely going to be up over 0.788, right? Yeah, it's not even close. So, yeah, so I get 0.966 plus 0.921 is approximately, well, 1.887. So it's very clear then that the cosine of 38 is not the same as the cosine of 15 and 23 added together. Okay, those two values are very different. And so as a general principle, as a general rule, I should say, the cosine of two angles added together is not equal to the cosine of each angle individually added together. Right, these two things are not equal to each other. However, there is a way to write the cosine of a plus b in terms of cosine of a and b. It's just not this straightforward. Okay, there's a different combination. Same thing for a subtraction. Right? If I had cosine of a minus b, then the cosine of a minus the cosine of b is not the same thing. These are not going to be replaceable. You can't substitute one expression in for the other. Okay, so that's something that cannot be done. What I'm going to do next is to help to derive. I'm not going to go through all the details of the derivation, but I'm going to help to give you an understanding of how or what the formula, what the proper formula is, and how it comes about, how it's derived. Okay, without maybe going through all of the algebra in that derivation. Okay, so I'm going to focus first of all on the cosine of a minus b, the cosine of the difference of two angles, and then we'll deal with the sum in a later video. So, let's see. So I'm looking for a formula then for the cosine of a minus b. That's what I'm looking for. Okay. Well, let's consider two scenarios. All right. I have an angle A positioned on two different unit circles. Okay, it's the blue angle up here. And I have another angle B just kind of randomly positioned here. It's a smaller angle. I'm just doing this. It doesn't really matter whether one is smaller than the other, but the images look nicer if B is smaller than A. It just kind of works out a little nicer. Okay, so I'm going to take angle B here, and I'm going to sort of transpose it onto these two images, but I'm going to put it in different locations. The first one here, I'm going to put angle B on the left side of angle A, all right? So angle B I'm going to put on the left, so it will look something like that, right? So angle B is this little guy in here. Oh, that didn't write very well. All right, so angle B, there it is, that looks better. So angle B is that little angle in there. So the result then is that if you take angle A and subtract angle B, the remaining angle, which would be this angle here, is going to be angle A minus B. That's the blue angle minus the green angle, okay? All right, so that's one way to geometrically represent A minus B. Now let's say I took that same angle B and I just stuck it on the other end of angle A. That's another valid option. So I put angle B over here on the right. Roughly, looks pretty good. There's angle B. So then again, if you take the angle A and you subtract off angle B, the stuff in between will be A minus B. Right, so that's going to be that stuff right there, right? That's A minus B. So there are two ways to show angle A minus B. Now, what's interesting, or what's going to be helpful, is the fact that I've got unit circles here, okay? So I've got the point 1, 0 on the x-axis, where the circle hits the x-axis. This has a radius of 1 all the way around. And I can find the coordinates of each of the points around the circles. Okay, so, for instance, on the circle on the right, the coordinates of the point on the unit circle at angle A will be found as the cosine of A, comma, sine of A. Now, how do I know that? Well, you'll recall the cosine and the sine are defined using the x, y, and r, x, y coordinates, and r as the hypotenuse, or the radius. Cosine is x over r, that's your adjacent over hypotenuse. Sine is y over r, that's your opposite over hypotenuse. But with a unit circle, the r value is 1. When you divide by 1, it doesn't change anything, so x over 1 is x, and y over 1 is y. And so that's how we find formulas for the x and y values on the unit circle. Okay, that works for the unit circle only. That's why that circle is so useful. Okay, so the coordinates of that point are the cosine of A, comma, sine of A. Likewise, the coordinates of the point on the right here where B ends is the cosine of A, comma, or I'm sorry, cosine of B, comma, sine of B. All right, so the angle changes there. On the other diagram, I have another point that I'm going to locate, and it is this point up here on the top left. And that point, now starting at the x-axis, the angle opens out to A minus B. So that point is the point cosine of A minus B, comma, well, I'm running out of room, comma, sine of A minus B. Let me give myself some more space here. So it's the cosine of A minus B, comma, sine of A minus B. Still ran out of room. Okay, there it is. Good enough. Okay, so those are three very important points. Okay, so cosine of A minus B, comma sine of A minus B, cosine A, sine A, cosine B, sine B. 3 points plus, and it's also this point 1 comma 0. Now, what's interesting is because the angle A minus B is the same here on the left as it is on the right, the arc length is the same. Okay, so this arc length from the point cos B sine B to cos A sine A, this arc length is exactly the same as the arc length from 1, 0 to cos A minus B sine A minus B. So this arc length here. Those two arc lengths are the same. Not only are the arc lengths the same, but also the chord is the same. A chord is the term used for the segment that connects 2 points on the edge of a circle, or on a circle. Okay. So the two chords are the same. The arc lengths are the same, the chords are the same, because the angles are the same and the radii are the same. Okay, so now what I can do is I can express the chords as the distance between 2 points on a circle. Distance between 2 points, period. Now, we know that the distance between 2 points can be found using the distance formula, which we've seen before. The distance formula uses the Pythagorean theorem, comes from the Pythagorean theorem, right? So if I were to consider the chord here, the distance is the distance from 1, 0 to this odd looking point here. And that distance is found by taking the square root of the change in x's squared plus the change in y's squared. Okay, that's how you get your Pythagorean theorem. So we want the change in the x's, which would be the cosine of A minus B minus 1. Right, that's the change in the x values, cosine A minus B and 1. Square that, so it's the change in the x's squared, plus the change in the y's squared. So that would be the sine of A minus B minus 0 squared, because those are the two y values. The change in x's, change in y's, that gives you the length and the height of the right triangle there, and the hypotenuse is found using the square root of the sum of the squares. Okay? So that's the first chord. Actually, I'm going to call that chord 1. Okay? Chord 2 is the one on the other side. Okay? Chord 2 is found also using a distance formula. It may not be quite that long, it might be. And it's going to be the cosine of A, so the same ideas. Change in the x's, change in the y's, square those, and add them together. So it's going to be cosine of A minus the cosine of B, all squared, plus, then we do the sine of A minus the sine of B. Again, all squared. Now, these two expressions, they're complicated, right? They've got square roots, they've got trig functions that are squared, lots of messy stuff. But you can set these equal to each other, right? The two chords must be equal because they represent the same angle and the same radius. Okay? And so if I set these two expressions, and here's where I'm going to skip over some of the algebra, just save some space and save some time. You can set these two expressions equal to each other, these two roots, then you square both sides, and then you kind of work through some of the algebra, expanding the parentheses out, canceling stuff that cancels, combining like terms, all that stuff. And eventually, you will get to a nice formula for the difference in the cosine, or the cosine of a difference. that formula is the cosine of a minus b equals, it's going to be the cosine of a times the cosine of b plus sine a sine b. Okay. So we can write the cosine of a minus b in terms of the cosine of a, the cosine of b, the sine of a, and the sine of b, but it has to take on this structure, okay, this formula. It's not an obvious formula, right? You have a minus inside, you have a plus on the outside, you have a combination of sines and cosines of a's and b's, products and sum in it. So it's not a real intuitive formula, but it is true. And so you can prove this by plugging in some numbers that we know. We could do like, I don't know, we could do like 90 and 60 or something like that. And we would find, you know, if we did 90 minus 60, you get 30. So the cosine of 30 should be the same as the cosine of 90, cosine of 60, plus sine 90, sine 60. So you could try it, you could verify it. I won't go through those details, but you could do that, and it would work out to be the same. You'd have the same value for both. Now, where I put these dot, dot, dot here, all the details of this derivation, the rest of that proof, it is actually located in your textbook. Okay, so for those of you who have the hard copy, those of you who have the ebook, it is on page 212 in your textbook. Okay, yeah. So that should get you this formula. Now there's also a formula for the cosine of a plus b. Okay. I was going to put that in another video, but I think I'm going to stick it on this one too. Yeah, might as well. It's not too bad. So let me get rid of some of this stuff, make myself some space. Not that I need a whole lot for this, but so this is a formula for the subtraction, for the difference. What's interesting is if you were to, you can actually use that formula and in order to get the cosine of a plus b, okay? You can use this formula, and I'll show you how. Consider this, the addition, as the subtraction of a negative, okay? So the cosine of a plus b is really the cosine of a minus negative b, right? Negative b is just as much an angle as b is, right? It's just opening in a different direction. Okay, so now, because I have this subtraction, it's really the difference of two angles, but instead of b, I just have to remember to use negative b everywhere there's a b in the formula. So I'm going to go to the formula. I'm going to take the cosine of the first angle times the cosine of now the second angle, which is negative b, not b. Okay, then I do plus the sine of a, the first angle, times the sine of the second angle, which was b, but now is negative b. Okay. Now, when you have the cosine of a negative angle and the sine of a negative angle, we had these things called even-odd fundamental identities. And they come from the fact that there's symmetry in the cosine and the sine function. The cosine is what we call an even function, and the negative on the inside kind of disappears, right? An even function for the cosine, cosine negative b is actually equal to the cosine of b. Those two things are equal. So we can make a substitution using a fundamental identity, using that even identity. So we have the cosine of a times the cosine of b, because cosine negative b and cosine of b are the same. The sine is an odd function, and with odd functions, the negative comes out. So we have the sine of negative b equal to negative sine of b. Okay, so remember, for an odd function, if the input has a different sign, then the output has a different sign. That was a key feature for an odd function. And so if I'm really multiplying here, instead of by sine of negative b, if I'm multiplying by the negative sine of b, which would be the equivalent, that negative, positive times a negative is negative, and so I can just move that negative and replace the plus here with the negative, right? Positive times a negative is negative. So I'm going to write this as cos A, cos B, minus sine A, sine B, okay? So, we've got this nice formula. It's similar to what we had before, except it has a minus in the middle. It's really the only difference, right? Everything else looks the same. So, let me write that up there in a nice succinct way like I had before. So the cosine of A plus B is equal to the cosine of A times the cosine of B minus the sine of A times the sine of B. All right. So we've got now two formulas, a formula for the cosine of a difference and the formula for the cosine of a sum. And these two formulas, they do look very similar. They're both the product of cosines on one term, the product of the sines on the other term. The formula for the difference has a sum in it, and the formula for the sum has a difference in it. That's the only difference, I guess. All right? Okay, so that gives us our two formulas. This whole section is basically based around those two formulas. So in the following videos, we're going to go through some examples that use these two formulas to either derive other formulas or to find other trig function values, of angles that we don't already know, things like maybe 15 degrees or something like that. Some expressions for angles that we don't know yet. Also, coming up in future sections, we're going to be looking at formulas for the sine of A plus B, and the sine of A minus B, and the tangent, and stuff like that. So all the other trig functions as well have variations of these formulas. Okay, and we'll talk about those later on, not in this section, but later.